let's calculate the electric potential generated by disk that's uniformly charged somewhere on the axis. And then, when we get that result, how about we use this idea to then, from the electric potential, get the electric field by just differentiating whatever expression we get for the electric potential. And it better matches what we derived, a few weeks ago. Yes? Can we do this then? Okay. So I'm teaching you yet another way of calculating electric fields by instead of going directly to k dq over r squared, and then it's a vector quantity that points away from the charge if the charge is positive, or towards the charge if the charge is negative. And then you gotta watch out about components that may cancel, and you might have a cosine of an angle, sine of an angle, right? That could be done. We've done it, right? We did it for the ring. We did it for the disk as well. So, and we did that, right? But you could also take this other approach. Instead of finding the electric field directly from the very beginning, just say, well, I'm going to find out what the electric potential is. That may be an easier integral to solve. And once you do that, then you get an expression for the electric potential as a function of some variable, and then the electric field is related to the electric potential by taking a derivative of it, right? So in the language over here is the gradient and the negative of the gradient, but you don't have to use that language, right? So, okay, so let's do this. So another example, now this is a disk. Of radius A and total charge Q uniformly distributed over the surface, right? Now it's distributed over the area. What is V generated by this charge somewhere on the axis of the disk at a distance x from the center of the disk? All right, so let me erase this. Okay, so we have the disk like this, and I'm interested in this point, distance x away from it. We have, now the total charge is Q, right, uniformly distributed. The area, the radius, of this thing is A, right? And what we do in this case is, let's calculate the electric potential over here. So now, the infinitesimal charge that we are going to consider is a charge distributed over a ring of radius r. Let me be consistent. Okay? And thickness dr. Infinitesimal thickness. So this thickness is very small. Very, very small. So small that over this thickness, I can think of the charge as being uniformly distributed. So that's r, and this is dr. Yes? And then from here, we have this distance. Now I have this other r. That's a different distance, r. And the charge in this ring of radius r, thickness dr, this charge is dq.
When you write the one R, is it like capital R?
I could use, I don't like to use this because usually that would be the radius. But I don't like to use that because very soon we're going to be talking about resistance, electrical resistance, and that's the symbol that we use for electrical resistance. So for the different radii, I like to call them A, B, C, D, and so I could call them capital R1, capital R2, capital R3. But very soon we'll be talking about resistance, and so I just kind of want to leave that for resistance, which is measured in ohms. And this, this thing like that, that's just me not being able to write straight. Okay? So the question is, what's the electric potential over there, right? Well, what is the electric potential over there generated by the charge in this ring? In this ring. I mean, and there are two ways that we can do this, actually. There are two ways that we can do this. Didn't I just calculate the electric potential generated by a ring? I can use that and apply it to this problem. Right? So remember that, let me show you how to do that in two ways. What did we say was the electric potential of a charge distributed over a ring of radius A at a distance x away from it, right? What did we say is the electric potential? It was K, Q, was it X over the square root of, oh, there was no X, right? That was for the electric field. It was just that, right? Is that right? Okay, that's it. And no vector, right? Because it's not a vector quantity. So, and this is a ring. So, we already did that problem, right? We could use this result to write down an expression for the potential over here, due to the charge in red in the ring of infinitesimal thickness dr. So let's call that dV. What would that be? Using that result applied to this problem, it would be what? It would be Coulomb's constant, K, times this Q over here is the charge in the ring. Now, in my ring over here, what is my charge Q? It's dQ. And this over here, x squared plus a squared, that was what? That was this distance, right? Yes? That's that distance, right? So over here, it would be, well, this distance r. Right? Because this was yes. Now, what is the Q? Well, how do I find the charge was uniformly distributed, right? So this charge dQ is distributed over an area. So I can say that the area of this ring with infinitesimal thickness dr, I'm going to call the area of this dA. So then, because of the uniform charge distribution, I can say that this charge, capital Q, is to the total area, which is pi a squared, right? That's the area of that surface. As the charge dQ is to the area over which dQ is distributed. Yes? Okay. Or if you like, you can say that this charge dQ is to the total charge as this area dA is to the total area. So I could also do it like that. I can say this charge in red is to all the charge as this area in red is to all the area. Or you could say this total charge Q is distributed over the area pi a squared. And this other charge dq is distributed over the area dA. So I can set up the proportions like that. Whichever way tickles you, go with that. Whichever way is going to make you happier, then use that. So I want to know what dq is, so I can solve for dq over here, right? I'll stick to this. So dq would be q over pi a squared times dA. And what did we say? Is the area in red? Remember the shortcut? Cut it, stretch it. What's the area of it? Two pi r dr. Length 2 pi r times the width dr. So this is that. So then this becomes dV is K, and instead of dQ, I'm going to write this expression here. It's actually, I can cancel these Q's, right? So it would be 2QR over A squared, and then I have this R here. Oh, and I forgot the R dr, so 2Q over A squared R dr divided by this on R, correct? But what is this R over here equal to? This is just the square root of correct? So let me know if I make a mistake. So this is 2K Q R dr A squared Have I made a mistake or no? No? Let's see. I think it looks good to me. So let me write that down over here. So we have dV equals 2KQ over A squared, right? And then we have R dr over the square root of R squared plus X squared, right? And that's the electric potential generated at this point in space, at this point on the axis of the ring, or disk, or this ring actually, and at distance x from the center, but just due to this ring in red. What I want, that's not what I want. What I want is the potential there due to all of the charge in the disk, which is obtained by adding the potential at that point due to this ring to the potential due to the next ring to the potential due to the next ring. Then I fill up this disk with rings. And that sum is done for me by simply doing this. And all of those are constants, so I'll just do this, right? So I get the integral here. This will be 2KQ over A squared. Now, and then I have R dr Now, here I'm integrating with respect to which variable?
R.
R. So my limits of integration must be values of R. And this R represents, is it the distance from the ring to the field point, or is it the radius of the ring?
Radius of the ring.
The radius of the ring. So if I imagine with the first ring, and then the next one, and then the next one, and then the next one, the next one, the next one, until I get the last one, I integrate from the radius of the ring equal to what? To the radius of the ring equal to what?
From 0 to A.
From 0 to A. And then what we need to do is solve that integral, which doesn't look so bad, right?
Just to use some.
You can say, okay, so I'm going to let the integral be r dr, r squared plus x squared square root, right? So you can let u be equal to r squared plus x squared. X is a constant, remember, right? And when you fix this point over here, that's a constant distance to the center. So what is the u dr? That would be 2r, right? So notice that I have an r dr over here. So from here, r times dr equals 1/2 of du. So this I can take and I can substitute in the numerator. And then in the denominator, I have the square root of u, which is u to the 1/2, right? So this would be 1/2 of u to the minus 1/2 du. And what is that integral? So I have 1/2, and then what? What's the integral of u to the minus 1/2 du?
2u. I mean 2 times u to the 1/2. I mean, yeah.
So it's u to the 1/2 divided by that same denominator, that same exponent, right? So this cancels that, and I just get the square root of u, which is the square root of, what did I let u? R squared plus x squared, right? So that's, yes. And now I want to put in my limits of integration. So I integrate from r equals 0 to r equals a. So this equals what? This would be the square root of x squared plus a squared minus, and then if I put a 0 in there, I'm just going to get an x. That's the value of the integral. Correct? Did I make a mistake?
Doesn't seem like it.
Not yet. So therefore, this is equal to 2k cubed over a squared times that integral, which is x squared plus a squared minus x. That's the expression for the electric potential, right? So the expression for the electric potential, it's going to be a function of x. It's going to be 2k cubed over a squared, right? Times, if you want to, you can write it like this. That's the answer. Questions? Next question. Yes?
Can you please say again why we should go from 0 to 8?
Because I'm integrating with respect to r, correct? So what is r in my picture over here? What does r represent? It's this r, not this other r, right? So I'm integrating with respect to this. And that r is the radius of this ring. So what I want is the contribution to the potential due to all this charge. And I can account for all of this charge by filling this disk with rings. Right? I can choose the first ring, that would have a radius of 0. And then the next ring, and then the next one, infinitesimal rings like this, right? And then the next one, and then the next one. The next ring, until I get the last ring. What's the radius of the last ring? 0A. Now the next question is this. What is the electric field over here? Generated by all that charge on that disk. Well, since we already have an expression for the electric potential, I could just take a derivative. Multiply by a minus sign, and put in the I hat, and that'll tell me the electric field at that point. Can I erase this?
Yes.
Yes, everyone? So if I want to know what is the electric field, right? So the question would be, so the electric field is minus, which is minus, and then this would be I hat dV dx plus J hat dV dy plus K hat dV dz. Now, does this electric potential depend on y? Does it depend on z? No, so those partial derivatives are 0. So now this becomes just an ordinary derivative. So it'll simply be equal to the derivative of this with respect to x. Multiplied by minus I hat, right? So this would be minus I hat. Now, what is the derivative of this expression with respect to x? So we have 2kq over a squared. That's a constant, right? Now, what's the derivative of this quantity with respect to x? What should I say? So what should I say? What's that? Okay, 1/2 times what? Raised to the, and then?
2x.
Times 2x. Minus, and what is the derivative of x with respect to x? 1. So notice, this 2 cancels this 2. This minus sign will cancel this minus sign if I multiply it through, right? So what I will get will be I hat
Excuse me, Professor.
2, and this is actually multiplying all of this, right? So it will be 2kq over a squared, and then I have 1 minus 2, actually the 2 cancels, right? So it's 1 minus x, and then this one, if I bring it downstairs, it'll be this. This should be the answer. Now look in your notes, 4 weeks ago or something like that, and tell me what did we get for the electric field at that point. And you can manipulate this quantity over here too. If you wanted to express this in terms of sigma, you could also say, 2kq over a squared could be written as 2k is 1 over 4 pi epsilon naught. Q is the charge per unit area times that area, which is pi a squared divided by a squared. So notice that this pi cancels that pi, this a squared cancels that, the 2 and the 4 gives me a 2. So this is just sigma over 2 epsilon naught. So you might see this also as sigma over 2 epsilon naught in your solution, depending on what I gave you back when we did this problem. Did I give you the total charge Q in the disk, or did I give you the charge per unit area sigma? So one could also express it in terms, if sigma is given, one could also say that this is I hat sigma over 2 epsilon naught 1 minus x over the square root of x squared plus a squared. And I can see that this is the correct result, because what would happen if I take the limit, instead of calculating the electric potential over here, suppose I get very close to the disk. Right? So then x is going to go to 0. In the denominator, I have 0 plus a squared. That'll be just the square root of a squared, which is just a. So this will be x over a, which is 0 over a. So this drops out, and the electric potential is just away from the disk. And sigma over 2 epsilon naught, which is the expression of an infinitely large sheet. If I'm very close to the ring, to the disk here, if I'm so close to it, this is going to look like it's infinitely large. And it's like I just have one sheet with charge sigma. Well, the electric field is sigma over 2 epsilon naught. That's what this result gives. So look at your notes. You can see that if I remember this problem, we, 4 weeks ago or something like that, we calculated the electric field directly. And we had to consider an electric field over here, which was a vector, and we had to consider the x component of it, and that threw an extra cosine of an angle in the integrand, and we had to deal with that. And I think I had to do a trigonometric substitution to solve the integral. Whereas in this case, to solve this integral, this is just u to the minus a half. I mean, that's something we can do right away. We don't have to do any trig substitution. So it's easier to solve the integral when you calculate first the electric potential, and then, it's just apply the chain rule and calculate the derivative, which is an easier step in general. Sometimes you're asked, find the electric field, and if you can apply Gauss's law, a couple of lines, you could be done. But if not, if the charge distribution doesn't satisfy the symmetry necessary for you to apply Gauss's law, then you have to integrate. The question is, you have a choice. You can choose to find the electric field directly by using k dq over r squared, right? And think of that as an electric field and consider the symmetry of the problem to see if some components cancel out. Or instead, you calculate the electric potential at that point, which might be an easier integral to solve, and then take the derivative of that to get the electric field. So this gives you an example of, if you know the electric potential, can you find the electric field? We could also go backwards, right? And to get the electric field from an electric potential, you gotta differentiate. And through what's called the gradient, and it's the negative of it, and so on. But what about if the problem is backwards? What if we have, for example, the electric field over some region of space? Maybe because we can apply Gauss's law and very quickly we can figure out the electric field. How do you find the electric potential? Right? So if knowing the electric potential, to get the electric field you have to take derivatives, what do you do if the step is backwards? If you know the electric field, how do you get the electric potential? What's the backwards step of taking derivatives?
Take an integral.
You gotta take an integral. Right? And let me show you some problems that you could do. I mean, we already did one, I think, last time for the potential difference between a set of parallel plates. But that was too easy because the electric field in this region between the two infinitely large parallel plates, it was uniform. So if she just came out of the integrand and, you just got delta V equals ED. So it was too easy. But let's see. How about we do problem number 3? Example number 3. So it says, a metal sphere, okay, let me erase this, you can read that if you like. So it says, a metal sphere of radius A with charge capital Q. So it's actually it should say a solid metal sphere. So charge is Q. Is surrounded by a thick concentric metallic shell. So it's a hollow thing of inner radius B and outer radius C. So now we have another metal. Radius B and outer radius C. So this is the other metal. So we have metal here, metal there, vacuum here, and a vacuum here. Okay, let's see what it says. The metallic shell carries no net charge. So the total charge of this is 0. Now, immediately, in less than 2 seconds, what is the charge on this surface? What is it? Just the charge Q. It's a metal. The charge goes to the surface. So this Q here will actually be on the surface, right? What is the charge on this surface here? This is one of those 1 second questions that you can answer in 1 second. What's the charge over here?
Negative Q.
Minus Q. And what's going to be the charge on this surface?
Positive Q.
Exactly. Because the sum of these two must be 0. This is one of those questions that, from the statement of the problem, you should know this like that. One more thing. What is the electric field in here? What is it? 0. And what is the electric field over here? 0. Can you tell me right away what the electric field is here? Can you do this problem in your head? Imagine I do a Gaussian surface. What's the electric field there? It would be just the total charge inside of that, which is? Over who? r squared. A cubed over r squared. And what's the electric field over here? Because my Gaussian surface is going to have radius r, not radius a. What's the electric field over here? What's the total charge inside of that? This is 0, and that's q, so it should be k cubed over r squared. But, that's... So, right away we should know a few things. So, first of all, the first question says, find the surface charge density sigma at radius A, at radius B, and at radius C. So what is sigma is the charge per unit area, right? So, A, what's the charge per unit area at radius A? So, what is the charge per unit area on the surface of the inner metal? What's the charge per unit area? What is the charge of this metal on the surface? Q. And what is the area over which is distributed?
4 pi r squared.
4 pi who?
A squared.
A squared. So it's just Q over 4 pi A squared. That's the answer. What is the charge per unit area on the inner surface of the shell, of the hollow sphere? What's the charge on that surface?
Negative q.
Negative q. And what is the area of that surface?
4 pi b squared.
4 pi who?
B squared.
B squared, correct. And what is sigma, the charge per unit area on the outer surface of the shell? Well, what's the charge on that shell? I mean, on that surface, I'm sorry.
Positive q.
Positive q. And what's the area of that?
4 pi c squared.
Exactly. As simple as that. Yes? Those are the charge densities at those surfaces, right? How much charge there would be distributed per meter square of area. Next question. B. Find the electric potential at the center. Ooh, interesting. I like it. What's the electric potential V right there? Now, do you want to do an integral k dq over r? Imagine you got this charge distributed. What's the electric potential at the center? So, let's work that out. So let me show you how to find it. There are two ways to do that problem. An easy way, and a more involved way. So I'm going to use the more involved method. So let me erase this. Okay. So pay attention to how I'm going to solve this problem. Okay? Basically, what I'm going to use is the following. If I want to know your age, there are a couple of ways that I can figure that out if I ask you a question and you answer me. One way is I can ask you, how old are you? And then you'll tell me, brr, whatever your age is, right? But another way that I can figure out how old you are is by asking you, when were you born? What year were you born? When is your birthday? And then you tell me the year that you were born, and we're in 2022. and I'll subtract out the year that you were born. And then figure out if you had a birthday this year already or not, right? In other words, I can find out your age by taking the difference, right, between the year that we're in and the year when you were 0, which was the day you were born, right? When you were 0 years old is what I meant to say, right? Yes? So what I'm going to do is this. I want to know the electric potential at this point, right? So I am going to find out the electric potential at that point, like your age, by finding the difference between the electric potential there and the location where the electric potential is 0, like when you were born. Yes? It's like I ask you, how high above are these keys from this table? Right? So you can take a ruler, right? And you say, what's the height on the surface of the table? 0. That's 0. That's 0 height. And then you measure the height over here, right? And then you subtract 0 to get the height of the thing above that. You're finding the height by finding the difference between the height here and the height at the location where the height is 0. So, I know it sounds weird, right? But that's essentially what I'm going to be doing. Right? So remember that electric potential, if you have a point charge, charge distribution, whatever, right? It's like K, some charge divided by some distance, right? Overall, it's going to have those distances, those units. At what location from Q is the potential 0? Where would it be 0?
Just that Q?
No, because there that would be KQ divided by 0. That's actually undefined, which is not the same thing as being 0. At what location, how far away from this point charge Q, will the potential be 0?
So far away, it like won't even matter.
Exactly. So it's like you gotta go to like, okay, if this is infinity, the potential there is gonna be 0. And that is what the problem states, right? It says, that's a hint. Using infinity as reference. In other words, I want to know what the potential is over here. But I know that at infinity, the potential is 0. Because I'm so far away from it, right? So essentially, I'm considering this. On a point here, let's say that's infinity. The potential there is 0, right? So, this is where I want to know what the potential is, right? How about I call that the potential at the center, 0. Not initial, but 0 radius, 0 distance from the center. So I know that the difference between these two, right, let me call this V and infinity. In other words, what I'm doing is this. If I calculate V naught minus V at infinity, because this is 0, that will just be that, which is what I want, right? That's like, 2022 minus the year you were born. Let's say you had a birthday in January, then it'll tell me your age. Yes? But how can I calculate potential differences? Well, if that's what I want, how about I do this? How about I do this? I put this over here, and I put this over here. If I evaluate that integral, what am I going to get? Am I not going to get what I want? Right? This is equal to this, which is equal to that, because this guy here is 0. Right? Or no? Now, what is this equal to? Then I go like this. dV is minus EdR. That's what we used last time, right? And then you integrate both sides, right? But what I want is this, right? So I'm going to put that up here, and I'm going to put this, the value of the electric potential that's equal to 0, which happens at infinity. But then remember how we must be careful to match limits, right? So this is an integral with respect to position, so what will be the value of r over here? Infinity, right? And what will be the value of r over here? 0. And if I don't want to use that minus sign, I can just flip this and say from 0 to infinity of e dr, right? And this will just be, because this is 0, this will just be this, right? So if I do this integral, I'll be done. Now, this electric field is in the integrand. It has to be the electric field between this point and this point, which means everywhere in space. So, given this problem, is it easy for me to figure out what the electric field is over here and what the electric field is over here? I already know that inside this metal, the electric field is 0, and inside this metal, the electric field is 0. All I need to do is figure out the electric field somewhere between the two metals and somewhere outside the two metals, and then I know the electric field everywhere from 0 to infinity. In fact, because the electric field is 0, then is something, then is 0, then is something, I can split up this integral into, I can integrate the electric field from r equals 0 to r equals, well, the surface of the inner conductor, plus the integral of the electric field from the surface of the inner conductor to the surface, to the inner surface of the outer conductor, plus from r equals b to r equals c. That will be inside the other conductor, right? Plus, and this is c, right? From r equals c to r equals infinity. Yes. Two of these integrals are 0. Where is the electric field equal to 0? Between 0 and A, because that's inside the metal. So that's this guy, right? Between 0 and A, the electric field is 0. And inside the other metal, the one that's hollow, right? From radius B to radius C, the electric field is 0, because it's inside another metal in electrostatic equilibrium. So then this guy is 0. So the integral is, the two integrals that I really want are from r equals 0, from r equals A to B, plus the integral from C to infinity, right? And just so you know which electric field is which, if I call the electric field here E1 and the electric field here outside E2, then E1 is between radius A and B, and E2 is between C and infinity. Now, can you get expressions for those electric fields using Gauss's law? Because this is, a problem where we have spheres. So let me do, yes? So suppose I want to know the electric field at this point, at a distance r. I draw my Gaussian surface. And what am I going to get? I'm going to say E1 times the area of that Gaussian surface, 4 pi r squared, equals, what is the total charge inside that Gaussian surface? Capital Q. So E1 equals 1 over 4 pi epsilon naught Q over r squared. So that will be this. Which is K Q over r squared. And what is this electric field E2? Well, if I want to know the electric field over here, and I draw a Gaussian surface like this, Gauss's law says take E multiplied by the area of the Gaussian surface, right? So that would be E2 times what is the area of that Gaussian surface, or radius r? 4 pi r squared equals, what is the total charge inside this Gaussian surface in green? Just Q, because this guy doesn't have any charge, so it's just Q, right? So I get the same result. E2 equals K Q over R squared. Of course, it's a different R, right? It's greater. So the calculation, therefore, to find the electric field at the center of the spheres is the integral from A to B of KQ over R squared dr plus the integral from C to infinity of KQ over R squared dr. Now, what is the integral of KQ over R squared? KQ is a constant, right? I can pull that out. What is the integral of the R over R squared? What's the integral of? Negative 1 over R, correct. From A to B plus. And then the other integral, which is, well, it's the same thing, right? KQ times negative 1 over R from C to infinity. So that would be KQ. Can I do this in one step? Right? I gotta put B over there and then A. When I put the A, it's a negative, so that'll make this a plus. So this will be 1 over A minus 1 over B. And then when I do this, 1 over infinity will be 0, but then the negative of the negative is gonna be plus. That's the potential at the center. That's the answer. Do I want to integrate K dq over R? Nah, I don't want to do that. Not for this geometry. It is easier to obtain the electric field in this case because I can apply Gauss's law and just a couple of lines I can get the electric field. And then use my knowledge of the electric field to get the electric potential by, well, instead of taking the derivative like you do when you take the gradient, when you calculate the electric field from the electric potential, now you go backwards. Well, you do that integral and you get the answer. Yes?
Can we calculate the potential on the surface of the smaller sphere?
Yes. And then you just, like if you want to know the potential over here, first of all, suppose you evaluate this and you get 2 volts. Suppose. What's the potential over here? Huh? 2 volts. Why? Exactly. So this would be 2 volts, 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 and on the surface, 2 volts. It will be equal to the potential at the surface. Because the electric potential is constant throughout the inside of the sphere and equal to the value of the surface. Then it's going to drop maybe 1.9, 1.8, ta, 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 ta. By the time you get here, let's say it's 1.5. And then 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, 1.5. And then 1.4, 1.3, 1.2. So by the time you get there, it's 0. It'll be like that. Dropping as 1 over R. No? So this is finding out the potential at some point. Like in this problem, as soon as I read it, I got spheres, you know, metals. Not only are there just spheres, but there are also metals, right? So I can easily obtain the electric field using Gauss's law, just a couple of lines. If I know the electric field, I can integrate that and I can get the potential at some point. What if the question is, what is the potential difference between A and C? Suppose the question is this. Suppose the potential on the surface of the inner sphere is, well, the potential at A, and on the outer surface the potential is, well, the potential at C. And I want to know the difference between them. Maybe you want VC minus VA, or maybe you want VA minus VC. How about we do VC minus VA? We can add this as a third question. Actually, is that a third question or no? Oh yeah, cool. The third question says, find the electric potential difference between the surface of the sphere, or radius A, and the metallic shell's outer surface, C. Oh, interesting. Except that they want it backwards. I would have. Okay, so part C. So what is VA minus VC equal to? Can I erase all of this? Maybe I'll just leave it there for the moment. So I want to know the difference in potentials. So how about I say I want VA minus VC, right? Wouldn't I get that if I do this? Is that right?
Yes.
Yes?
Yes.
But then this is minus EDR, and then this is R at here, which is A, and this is R at C. Can you see how I'm building my problem to solve? So VA minus VC equals, and I can get rid of that minus sign if I don't like it, by integrating from R equals A to R equals C. Now, so this means I want the electric field between the surface with radius A and the surface with radius C. Let me clean it up a little bit so it's easier to see. We have radius A, radius B, radius C. Metal, metal. I need to know the electric field between A and C. So I need to know the electric field between this point and this point. And that's the electric field that I need to know. Well, I know that over this region here, the electric field is 0, because I'm inside that metal. Right? So the integral from B to C is going to be 0. And then what about in this region? What is the electric field over here? Well, once I step outside this sphere, the electric field is the same as if all the charges distributed at the center. So that's like what I did over there, E1, right? That's KQ over R squared. So I know the electric field between A and B and between B and C. So this integral from A to C, I'll break it up into two integrals because the electric field here is given by one expression and there is given by another expression. So VA minus VC equals EDR from A to B plus from B to C EDR. But the electric field between B and C is 0, right? Because the electric field here is 0, right? And the electric field between A and B It's E1. So this just equals the integral from A to B of KQ over R squared dr. And then I just do that integral, right? Then it's, you know, a piece of cake. That's the answer. That's the potential difference between those 2 points, between those 2 surfaces. So the potential difference between what was that VA minus VC is KQ Now, let's check something. When you evaluate this, should it be positive or should it be negative? Now, don't look over here. Don't look. Should it be positive or should it be negative? Right? So there's no electric field over there. What about in this region? Which way is the electric field pointing? This was a plus Q here, right? So electric field is pointing this way. Right? So which of these 2 surfaces, this one or this one, is at the higher electric potential? What happens when you walk in the same direction as the electric field? What happens to the electric potential? Does it get bigger or smaller? Smaller. So that means that the potential at A, which is here, has to be bigger than the potential at C. Because the electric field is in that direction, right? So this better be positive. Now let's check the algebra. These 2 are positive. Now 1 over A minus 1 over B. Which of these 2 radii is bigger? A or B?
B is big.
B. So therefore this is smaller, right? Because you're dividing 1 by it, right? So this is small. This is big, or at least bigger than that. So this difference is going to be plus. So it'll be, you know, it'll be plus. I'm good. So I can check that. Questions? And I have other problems here. This. Should I do number 1? Now that one is just point charges, right? So just get you over R. By the way, this expression for the gradient E equals minus the gradient of V, that's when when you have electrostatic, you charge something and then you leave it alone and the charge just stays there. All right, so example number 1. So what do we have? We have 3-point charges, 1, 2, 3. So 1, 2, oops, I said 2, but I wrote 3, and 3. We have some distances here, right? 3 and 4, that's easy, convenient. And we're given these charges, right? Q1 is 2 microcoulombs plus, so this is plus 2 microcoulombs. Q2 is minus 6 microcoulombs, and Q3 is 3 microcoulombs plus 3. So this is positive, positive, and negative. Okay, find the electric potential at the fourth empty corner of this rectangle. So what is the electric potential here? So this is 4 meters, 3 meters. Well, what do we have? We have 3-point charges. How do you find the electric potential of a point charge? What's the formula for the electric potential generated by a point charge at a distance r away? K over r. So this would be KQ1 over R1 plus KQ2 over R2. No need to integrate over here. The charge is not distributed over something. So it's just easier to use the formula for this, right? K is what? 9 times 10 to the 9th. Q1 is 2 microcoulombs. 2 times 10 to the minus 6. And how much is R? From Q1 to the field point is what?
5.
5 meters. So you just divide by 5. Don't square it. We're not calculating electric fields. We're doing electric potential, right? Plus 9 times 10 to the 9. Q2 is what? Minus 6 times 10 to the minus 6. And what is R for Q2? What is it? 4, correct. Correct. And then 9 times 10 to the 9th. Q3 is 3 microcoulombs, so 3 times 10 to the minus 6. And what do I divide by? 3. And you have fun with your calculator and you get an answer. Which I don't know if I calculated. Or maybe I did. I think I got minus 900 volts. Next question. Notice, I never drew arrows, no vectors away towards this. Electric potential is not a vector quantity, right? It's a scalar quantity. The only way to account for this negative sign is to actually put it in there. You gotta put it in there. It's the only way to account for it. The other two are positive. The distances are always positive, right? Okay, next question. Find the electric potential energy of Q3. So what is the electrical potential energy of Q3? I want to know the energy of this baby right here. So what should I write down? What is the formula for the electric potential energy of a point charge? It's Q3, the point charge, multiplied by what?
V.
By V. V where?
At
Do I want V here?
No.
V here? It's where Q3 is. But what's generating the point charge over there? 1 and 2. Not Q3, because then I would have to say Q3 divided by 0. It's undefined. So this I have to multiply by V, at the location of Q3 generated, well, by the other charges in the problem, by the other charges, the external charges to Q3, by Q1 and Q2. So this would be Q3 times what? K Q1 over R1 plus K Q2 over R2. So I want the potential there generated by these two guys over here. So this is. So what is the charge of Q3? It's 3 microcoulombs. And what is the electric potential here generated by these 2-point charges? Well, Q1 is going to be K Q1 divided by 4, right? So it would be K, 9 times 10 to the 9th. Q1 is 2 microcoulombs divided by the distance from Q1 to where Q3 is located, which is 4. Plus the potential at Q3 generated by the other charge, by Q2, which is K, 9 times 10 to the 9, times Q2, which is minus 6 microcoulombs, divided by the distance from Q2 to Q3, which is also 5 meters, right? Divided by 5. And then you take out your calculator and you evaluate that. And I think this is minus 1.89 times 10 to the minus 2. So this is minus 1.89 times 10 to the minus 2 joules. So that would be minus 18.9 times 10 to the minus 3 joules. So let's just say minus 18.9 millijoules. Or if you like, you can express it in terms of joules. And there's a third question. If you can, double check that calculator work over there and let me know if it's correct or wrong. There's a third question. Let me put it up. It's an interesting question. It says, find the potential energy of the whole assembly. And really what that is asking is, imagine that there's nothing in here, and you bring in Q1, and you do work to do that. Actually, you won't do work if you just bring Q1, with the others not there. But then you bring it, and you bring it from infinity, and then you bring in Q2, and that will be interacting with the electric field of Q1. And then you put that over there. And then once you have Q1 and Q2, now you're bringing from infinity Q3. And how much work did you have to do that? What was the energy that you had to put into the system? So what is the total potential energy of the system? Right? So the way to do it is like this. You say, let me calculate the energy of Q1 as it interacts with 2 and 3, plus the energy of Q2 as it interacts with 1 and 3. But I already counted its energy of interaction with Q1. And then Q3, the energy of that as it interacts with 2 and 3. But you don't want to double count. So the way to not double count, right? Notice that these expressions are, it's a point charge, and then you multiply the 2 charges divided by R. Coulomb's constant, and then you multiply 2 charges divided by R between them. This is really between 1 and 3, and this is between 2 and 3. you just, so this is 1 interacting with 3 and 2 interacting with 3. Because this guy is interacting with this 2. So let me just write down an expression. You'll see the expression that I'm going to write down. But I don't want to double count. So I'll say, okay, so the energy of the whole assembly is K Q1 interacting with Q2 divided by R12, the distance between 1 and 2. Plus K Q1 interacting with Q3, well, and divided by the distance between 1 and 3. Plus, whose energies am I leaving out so far? The energy of interaction between what and what? Between 2 and 3. So this will be K, Q2, Q3, R23. And I think I have all of them accounted for. 1 with, see, this is 1 with 2, 1 with 3, 2 and 3. So then you say, okay, so this is 9 times 10 to the 9th. Q1 is 2 microcoulombs, 2 times 10 to the minus 6, and Q2 is minus 6, so it's minus 6 times 10 to the minus 6. And what is the distance between 1 and 2? It's 3. Plus. Now, that one is going to be, I'm going to write it over here, 9 times 10 to the 9th. What is Q1? 2 times 10 to the minus 6. And what is Q3? 3 times 10 to the minus 6, positive. Divided by, what's the distance between 1 and 3? 4. Plus, and what is the energy of interaction between 2 and 3? So it's 9 times 10 to the 9th. Q2 is minus 6 times 10 to the minus 6. And Q3 is 3 times 10 to the minus 6. And what is the distance between 2 and 3?
5.
5. That way, I have accounted for the interaction of every charge with every other charge, but without double counting. And it looks like it's minus 0.0549 joules, which you can write as minus 54.9 millijoules. This expression for the potential energy of interaction between two charges, and if you just consider this, that's analogous to, suppose you have a mass over here m1 and another mass over here m2 separated by a distance r. What is the gravitational potential energy between these two masses, these 2 point masses? What is the expression for gravitational potential energy? So it's minus capital G m1 m2 divided by the separation distance between them. Now, what if you have a bunch of these? What if you have, for example, m1, m2, and m3, and this distance is r12, this distance is r13, and this distance is r23. And I want to know, what is the total gravitational potential energy of interaction between all of them? So in that case, you would say, well, it's minus g m1 m2 over r12 plus the interaction of, that was 1 with 2, what about 1 with 3? Plus, but that's negative, right? So minus g m1, m3, r13 plus, what am I missing? The interaction between 2 and 3. So it's minus m2, m3 divided by r23. And I have accounted for all the interactions between them. This one, 1 and 2, 1 and 3, 2 and 3. So that would be the total energy of interaction, gravitational potential energy in that case. Yes. So this is something that I said, that I mentioned in my notes. So I'm gonna stop here. What in my notes, I said electric potential energy. So, see, what is the potential energy of an assembly of point charges? So here I have 3 of them, right? Actually, I have 3 point charges and I want to know the electric potential over there. So it's KQ1 over R1 plus KQ2 over R2, but that was the question of finding the electric potential energy here. So we did that. Now, and then we did that, blah. Now, what about over here? What is the energy of an assembly of point charges? Here it's better because I have Q1, Q2, Q3, and Q4. So what is the total electrical potential energy of this assembly of point charges? So I just wrote, well, 1 interacts with 2, with 3, and with 4. So this is 1 and 2, 1 and 3, 1 and 4. But then 2 interacts with 1, but I already took that into account. So I gotta account its interaction with 3 and 4. So Q2 with 3, Q2 and 4. And then Q3 interacts with all of them, but I already accounted its interaction with 1 and 2. Q3 with 1, Q3 with 2. So I'm only left with this one, so that's Q3, Q4. So this is what I just did in part C over here for just 3 charges, as opposed to 4 point charges. I guess it's easier when you write many of them. So notice I don't double count. So I'm done with this chapter. So after chapters 21, 22, 23, you need to take a test. Do you want it this Wednesday?
No.
So next Monday? So this Wednesday, you ask me questions. Let's review. Ask me questions. So, and then, so exam number 1. Next Monday on chapters 21 through 23. Only 3 chapters, but as you can see, I decided to do that because there's a lot in these chapters, right? So 3 chapters is enough. And then the next test will cover 24, 25, 26, and probably 28. And then the last exam, which is the final, will be 27, 29, 30, whatever we have left. So it's not going to be cumulative. And I'm going to choose 4 problems in this test. Each problem 15 points. I haven't decided yet if I'm going to put, so I have 3 chapters and 4 problems. So there's going to be a problem from 2 of the chapters and 2 problems from 1 of them. I just haven't decided, which one goes with what. But just 4 problems, part A, B, probably A, B, C. Know how to do the examples that I've done, homework problems as well. What we'll do after this is, after that exam, we're going to begin to talk about circuits. And we're going to talk about capacitors. And then electric current, Ohm's law, and current measurements, voltage, resistance. And then DC circuits, like if you have a battery with a lot of resistors connected in series, in parallel. So we're gonna launch now into circuits. So these 3 chapters will be on circuits, and then we'll talk about magnetism. magnetic fields, magnetic forces, right? And then connections between electric fields and magnetic fields. Right? This chapter over here discusses how from a magnetic field that's changing over time leads to an electric field. Okay, so then we're going to do this, and there's a couple more chapters in there, but exam number 2 will be on this, and probably chapter. I jump from 26 to 28, and then I go to 27. So the next test will be 24, 25, 26, 28, and then the final exam will be 27, 29, and whatever we cover over here. Chances are that we're not going to get to chapter 31, but I'll say something about it. I like to talk about electromagnetic waves. So, But again, each test 4 problems. Okay.
Do you think that we'll touch on 24 at all Wednesday? Or is it
It's up to you if you bombard. Well, I don't want to use that word, especially these days. If you have a lot of questions, I'll just answer your questions. If you have no questions, then we'll move on to 24. Okay? And also next week, because you have an exam, then the lab that we do this week won't be due next week, but the week after that. Yeah? So you do a lab this week, but you can just collect data. Actually, the next 2 experiments are going to be simulations, so we'll go over them here, collect the data, right? Understand what you're doing, and then you can write up those reports after the test.
Will we have a lab next week?
Yeah. It's another simulation. The next 2, I think, are simulations. I have an interesting lab on Ohm's law, but I don't want to do labs on Ohm's law if you don't know what it is. And there's also a lab where we have a resistor connected in series with a capacitor, and we derive an expression for the charge as a function of time as the capacitor charges. And we have that lab, but for that we need to finish 24 and 25 or 26. So those labs I like to do. When you're ready to do them, then you get more out of them. And then they'll become very simple. Otherwise, they'll be like, what is this? So I'll just fill in with a couple of simulations, which shouldn't take long to do. And some of them are nice. They're different from a lab. Auf Wiedersehen. Yes?
So the lab today, since you're just going over the simulation, is it going to be like how it was during Zoom, just like really short?
Yeah, so I'll go over it. You can probably, take in data with the simulations. It's quick, so you should do that, right? If you have any questions, then I can help you with it. But you can write it up. Yeah, so I don't expect you to be there longer than an hour and a half.